Thus, when we melt solid, some disorder is introduced in the liquid obtained, but this disorder is much smaller than the disorder introduced when we change the same amount of liquid melt to the vapor at the boiling point. This again shows that the constituent particles of a liquid are not as ordered as that in a solid, but at the same time they are not as disordered as that in a gas. Third, X-ray diffraction studies. X-ray diffraction studies of crystalline solid shows that the constituent particles within the solid crystal are arranged in a perfect order, and this order extends up to the edges of the crystal. This is called long-range order. Electron diffraction studies of gases shows that the gaseous molecules have no order at all. There is a totally chaotic motion of the molecules. The structure of liquids is also studied with the help of X-ray or neutron diffraction methods so that they can enter into the interior bulk of the liquid rather than being reflected only from the surface. If, like gases, the molecules in a liquid had absolutely no ordered arrangement, there would be a continuous scattering of X-ray diffraction, X-ray rays without maxima or minima. However, this is not the case. For example, the X-ray diffraction pattern of liquid mercury shown in figure 2.7a. This diffraction pattern shows that there are one or two diffraction maxima at small angles, but as we move outwards from some centrally chosen atom, the maxima are damped out. This shows that in the liquid law, short-range order still exists, but there is no long-range order. It is convenient to study the location of particles in a liquid in terms of radial distribution function, which gives the probability of finding an particle in the range dr at a distance r from another. These are easily calculated from X-ray diffraction pattern. In these cases, only the distance of the neighboring molecules, not the angles from the centrally chosen one, are studied. The radial distribution curves calculated of the scattering curve is shown in figure 2.7b. 2.4 Theories or models of liquid state. Gases and solids are two extreme states of matter. In the former, there is a total chaos of molecules, while in the latter, there is a perfect order arrangement of its particles which keeps on vibrating about their mean position. In both cases, the mathematical treatment becomes easy, and well advanced theories have been put forward to calculate their properties, that is, energy, heat capacity, entropy. However, in the case of liquids, the situation is not well defined. That is, the cohesive forces are sufficiently strong so that they can exist in the condensed state, but not strong enough to hold the particles in the fixed position so that they do have some translational energy. Hence, their theories are difficult to handle mathematically. The two common theories about liquids are briefly described below. Vacancy or hole theory. This theory was put forward by Eyring and Rey in 1933. This theory is based on the fact that liquids are generally less dense than the corresponding solids. This implies that the intermolecular space in a liquid is more than that in a solid. Eyring and Rey put forward the important view that in a liquid the intermolecular space is not random but comprises of holes or vacancies of the size of molecular diameters. Thus, a liquid can be considered to consist of liquid molecules and the holes randomly distributed between them. Due to the presence of holes, the neighboring molecules can easily jump into them and thus shows gas-like behavior. Those molecules which do not have a hole in the neighborhood cannot jump and hence show solid-like behavior. Using appropriate mathematical treatment, the mole fractions of the gas-like and solid-like molecules can be calculated. From these values, the thermodynamic properties of the liquid can be calculated. The results thus obtained for argon by Eyring and Rey were found to be in close agreement with the experimental values. Free volume theory. According to this theory, it is believed that a molecule in a liquid is surrounded by 10 to 12 neighboring molecules only a small distance away from the molecule. These surrounding molecules thus forms a cage-like structure or cell around the neutral molecule as shown in the figure 2.9. Thus, the central molecule has to move only through a small distance to collide with any of its neighboring molecules, unlike in a gas, where the molecules has to travel a long distance before colliding with another molecule. Thus, the center of the caged molecule can move within the space shown by the shaded area. The volume thus available to a molecule within which its center can move is called the free volume. Assuming the potential field within the cage or cell is spherically symmetrical, free volume can be calculated, and this can be related to various thermodynamic properties of the liquid. 2.5 Structural differences between solids, liquids, and gases. The main point of difference between a solid, liquid, and a gas are summed up in the table 2.1 given below. Solid. Their X-ray diffraction patterns have well-defined maxima. The constituent particles are arranged in a perfect order, that is, there is a short range as well as a long range order. The constituent particles are very closely packed, hence they show strong intermolecular forces of attraction and hence possess rigidity and a definite volume. The constituent particles have no translational or rotational motion, however, they have vibrational motion. Solids have high density. Liquid, their X-ray diffraction patterns have only one or two well-defined maxima, which damp out with distance. There exists a short-range order, but there is no long-range order. The molecules are separated by small distances, though the forces of attraction are weaker than solids but are sufficient enough to hold them together. Hence, they show fluidity and have a definite volume but no definite shape. Their molecules have some translational, rotational, and vibrational motion. Density of liquids is lower than that of a solids but higher than that of a gases. Gas. Their electron diffraction patterns do not have any maxima. There is neither short range nor a long range order. Rather, there is a chaos of molecules. The molecules are separated by large distances, hence, the intermolecular forces of attraction are weak. As a result, they have neither definite shape nor definite volume. Their molecules have large translational, rotational, and vibrational motion. Gases have low density. 2.6 Physical properties of liquids. A general introduction. We have already studied about gases in chapter 1. Liquid differ from gases in one important aspect, that is in the state of aggregation of their molecules. In the liquids, the intermolecular distances are not as large as in the cases of gases. As a result, the intermolecular forces of attraction in case of liquids are much larger as compared to those in case of gases. Consequently, although like gases, the liquids have no definite shape, but unlike gases, they have a definite volume. Because of the difference between the gases and the liquids as noted above, the liquids do not obey any general laws as is done by the gases. However, the liquids possess certain physical properties which are characteristic of each liquid. These properties helps us to decide the chemical constitution of the liquid. Some of the common physical properties of liquids are vapor pressure, surface tension, viscosity, refractive index, optical activity, dipole moment. Now we shall take up the discussion of first four properties one by one. Vapor pressure. Definition. Suppose some liquid is placed in an evacuated vessel connected to manometer as shown in figure 2.1. 2.10. According to kinetic theory of liquids, the molecules of the liquid are constantly moving in different directions with different speeds. Thus, as these molecules are moving with different speeds, they possess different kinetic energies. At any particular temperature, the energy of some of the molecules may be so high that they may leave the liquid and come in space above the liquid. This process is called evaporation. As the same as the time passes, more and more molecules of the liquid leave the liquid. As the time passes, more and more molecules may leave the liquid and come in the space above the liquid. This process is called evaporation. This process is called evaporation. As the time passes, more and more molecules of the liquid leave the liquid and come in the space above the liquid. The molecules thus present above the liquid are called vapor. The molecules in the vapor phase are also constantly moving, and some of them strike the surface of the liquid and may be recaptured by the liquid. This process is called condensation. If the liquid is added into the evacuated vessel, then initially, as there are no molecules of the vapor, the rate of condensation is zero. However, if the temperature is kept constant, the evaporation continues at constant rate as shown in figure 2.11 by the straight line plot. Now, with the passage of time, as the number of molecules in the vapor phase becomes more and more, the rate of condensation also increases as shown in figure 2.11. Ultimately, a stage is reached when rate of condensation becomes equal to the rate of evaporation, that is, as many molecules re-enter into the liquid as leave the liquid in the same time. This state is called the state of equilibrium. The pressure exerted by the vapor at this stage, as indicated on the manometer, is called the vapor pressure, or sometimes called the saturated vapor pressure, as the vapor phase is saturated with the vapor at this stage. Hence, vapor pressure of a liquid at any temperature may be defined as the pressure exerted by the vapor present above the liquid in equilibrium with the liquid at that temperature. 2.7.2 Some important results. Some important results related with the process of evaporation as given below. 1. Cooling caused by evaporation. When a liquid evaporates, the more energetic molecules leave the liquid. As a result, the average kinetic energy of the remaining liquid decreases and hence the temperature falls. Second, factors affecting vapor pressure. Two important factors on which the vapor pressure of the liquid depends are: first is the nature of the liquid. If the intermolecular forces of attraction in the liquid are weak, the molecules can easily leave the liquid and come into the vapor phase, and hence the vapor pressure is higher. For example, the vapor pressure of ether, acetone, benzene is higher than that of water at the same temperature. Second effect of temperature: as the temperature of a liquid is increased, the number of molecules with higher kinetic energy increases, hence the vapor pressure of the liquid increases. This is evident from each curve given in the figure 2.12. The effect of temperature on the vapor pressure can be studied quantitatively with the help of a Clapeyron equation. For the vaporization of a liquid, the equation is written in the form dP by dt is equal to d delta HV upon T V minus V, where delta HV is equal to latent heat of vaporization of the liquid, VV is equal to molar volume of the vapor at temperature T, VL is equal to molar volume of the liquid at temperature T. As VL is very small as compared to VV, neglecting VL in comparison to VV, equation 1 given above takes the form dP by dt is equal to delta HV upon TVV. Equation number 2. Further assuming that vapor behave like an ideal gas, we have PVV is equal to RT, or VV is equal to RT upon P. Substituting this equation in equation 2 point, substituting this value in equation 2.2, we get dP by dt is equal to delta HV upon RT square P, or 1 upon P dP by dt is equal to delta HV upon RT square, or d of ln P upon dt is equal to delta HV upon RT square. This equation is called the Clausius-Clapeyron equation. This is commonly expressed in another form called integrated form as derived below. That is, equation 3 may be written as, equation 3 was d ln P upon dt is equal to delta HV upon RT square. This may be rewritten as d ln P is equal to delta HV upon RT square dt. If the vapor pressure changes from P1 to P2, when temperature changes from T1 to T2, then integrated equation 4 between the appropriate limits, we get integration P1 to P2 d ln P is equal to temperature T1 to T2 delta HV upon RT square dt. Ln P2 upon P1 is equal to delta HV upon R. Integration T1 to T2 1 upon T square dt is equal to delta HV upon R 1 minus T1 minus 1 upon T1 minus 1 upon T2. Log P2 upon P1 is equal to delta HV upon 2.303 R into T2 minus T1 upon T1 T2. Boiling point. As stated above, the vapor pressure of a liquid increases as the temperature is increased. The temperature at which the vapor pressure of the liquid becomes equal to the external pressure, that is the atmospheric pressure, is called the boiling point of the liquid. When the external pressure is normal atmospheric pressure, that is the 760 mm, the boiling point is called the normal boiling point. For example, normal boiling point of the water is 100 degrees Celsius. The normal boiling point for any liquid is obtained from the vapor pressure temperature curves as shown for acetic acid in figure 2.12. Obviously, if the external pressure is higher, more heat will be required to make the vapor pressure equal to the external pressure, and hence heat higher will be the boiling point. Similarly, if the external pressure is decreased, the boiling point is lowered. This is the reason that a liquid boils at a temperature lower on the top of a mountain where pressure is low than on the seashore. Fourth, heat vaporization. When the liquid starts boiling, if extra heat is applied to the liquid, it is used up not in increasing the temperature of the liquid, but to overcome the intermolecular forces of attraction existing in the liquid and thus changing the liquid into vapor. Hence, the temperature remains constant till whole of the liquid changes into vapor. The amount of heat required to change 1 mole of a liquid into its vapor at the Boiling point is called the heat of vaporization of the liquid. Obviously, greater the intermolecular forces of attraction present in the liquid, greater is the heat of vaporization. For example, the heat of vaporization of water is more than that of ether, acetone, benzene. Relationship between boiling point and critical temperature, that is Goldberg's rule. Goldberg in 1890 pointed out that the following general relationship between the normal boiling point Tb and the critical temperature Tc of liquids exists, that is Tb is equal to 2 by 3 Tc. That is, the normal boiling point of the liquid are nearly two-thirds of their critical temperatures when both are expressed on the absolute scale. Relationship between boiling point and the heat of vaporization, that is Troughton's rule. Troughton in 1884 observed the following generalization about liquids which are non-associated and which do not have too high boiling points, where delta HV is in calories and TB is in degree absolute. This is known as Troughton's rule and may be stated as follows. For liquids which are non-associated and do not have too high boiling points, the ratio of heat of vaporization expressed in calories to the boiling point expressed in degree absolute is approximately 21. 2.7.3 Measurement of vapor pressure. The various methods used for the measurement of vapor pressure are generally classified into two categories. One is static methods and the second one is dynamic methods. These methods have been so named because in the static methods, the liquid is allowed to establish its vapor pressure without being disturbed, while in the dynamic methods, the liquid is disturbed either by cooling it or by passing a stream of inert gases through it. Some commonly employed static and dynamic methods are briefly described below. One is static method, that is, first of all, A. Barometric method. In this method, two barometric tubes are used. These are filled with mercury and then inverted into the trough of mercury. One tube is used for the comparison with the other. In one of the tubes, the experimental liquid free from dissolved air is introduced a few drops at a time. It evaporates into the space above mercury. More and more of the liquid is introduced till no more liquid evaporates and remains as such. Till the difference of levels of mercury in the two tubes is then the vapor pressure of the liquid at the room temperature. For finding the vapor pressure at any other temperature, the barometric tubes are surrounded by a heating jacket as shown in figure 2.13. B. Isoteniscope method. This method was devised by Smish and Menzies in 1910. It is a convenient method and accurate method which can be used to measure the vapor pressure over a range of temperatures. That apparatus is shown in figure 2.14. The main part of the apparatus is the isoteniscope, which comprises of a bulb B and U-shaped portion of the tube C. The bulb B is nearly half filled with the liquid under investigation, and the same liquid is placed in the U-shaped position with its level up to about 2 to 3 centimeter below that in the bulb. The isoteniscope is placed in the thermostat A, whose temperature can be noted from the thermometer T. The isoteniscope is then connected to the rest of the apparatus, which comprises of a barometric tube D and a big bottle E, as shown in figure 2.14. The bottle E can be connected to the atmosphere or to the vacuum pump as desired, so as to regulate the pressure inside the apparatus. The method involves the following steps. The bottle E is connected to the vacuum pump and the apparatus is evacuated till the liquid boils vigorously in the bulb B. This expels all air from the isoteniscope PC. The level of the liquid in the limb L2 stands higher than that in the limb L1. The temperature of the thermostat is now adjusted to the desired value and air is admitted slowly into the apparatus by connecting the bottle E to the atmosphere till the level of the liquids in both the limbs L1 and L2 are equal. Under these conditions, the pressure in both the limbs L1 and L2 will be equal. Pressure in the limb L1 is the vapor pressure, whereas pressure in the limb L2 is equal to the pressure in the rest of the apparatus and is equal to the atmospheric pressure in centimeter minus the height of mercury column in the tube D in centimeter. Hence, this difference is the vapor pressure of the liquid at the temperature of the thermostat. By fixing the temperature of thermostat at any desired value, the vapor pressure can be measured at that temperature by repeating the process as described above. Dynamic method. The simplest dynamic method is based upon the principle that a liquid boils at the temperature at which the vapor pressure becomes equal to the external pressure over the liquid. Thus, by fixing the external pressure over the liquid at different values, the boiling point of the liquid is determined at each external pressure. Suppose the boiling point are T1, T2, T3, etc. at the external pressure P1, P2, P3, etc. respectively. And obviously, the pressures P1, P2, P3 will be the vapor pressure at the temperatures T1, T2, T3 respectively. By plotting the pressures against the corresponding temperatures for any particular liquid, a curve of the type shown in figure 2.12 is obtained. From this curve, the vapor pressure at any temperature can be found. Thus, the dynamic method differs from the isotoniscope method in the aspect that whereas in the isotoniscope method, the temperature is fixed first and then the vapor pressure is measured. In the dynamic method, the external pressure is fixed first and then the liquid is heated to find the temperature at which it boils. That is, third is gas saturation method. The basic principle of this method is briefly described below. A known weight of the experimental liquid is taken in a closed vessel. A known volume of the dry air at a known pressure and a temperature is then passed into it. As a result, the molecules of the liquid are carried with the air and a loss of weight of the liquid occurs. Air is continuously passed till there is no further loss in the weight of the liquid, keeping the pressure P constant throughout. The air gets saturated with the vapor. In the air saturated with the vapor, if N1 and N2 are the number of moles of the vapor and air respectively, then the partial pressures of the vapor, which is equal to the vapor pressure of the liquid at the experimental temperature, will be given by P is equal to N1 upon N1 plus N2 into P. If W is the loss in weight of the liquid and M is its molecular mass, then N1 is equal to W upon M. Further, if air is supposed to be an ideal gas, N2 is equal to PV upon RT. Substituting the values of N1 and N2 in equation 1, the vapor pressure of the liquid can be calculated at the desired temperature. Instead of dry air, any gas like nitrogen which does not react with the liquid can be used. Thus at 310 Kelvin, P is equal to 2.8 surface tension. 2.8.1 definition. Surface tension is a characteristic property of liquids which arises due to the fact that the molecules of a liquid at the surface are in a different situation than those in the interior of the liquid. For example, a molecule lying inside the liquid is surrounded by other molecules and so is attracted equally in all directions, since the net force of attraction acting on the acting on the molecule is zero. However, a molecule lying at the surface is attracted more by the molecules lying in the bulk of the liquid than by the molecules lying above it in the vapor phase. Thus, a molecule lying at the surface experiences a net inward attraction. As a result of this inward pull on the all molecules lying at the surface behaves as if it were under tension, like a stretched membrane. Hence, this property of liquids is called surface tension. The surface tension of a liquid is defined as the force acting at the right angles to the surface along 1 centimeter length of the surface. Thus, the unit of surface tension are dynes per centimeter or newtons per meter in the SI system. Further, as the result of the inward pull on the molecules at the surface of the liquid tends to contract to the smallest possible area for a given volume of liquid. It is for this reason that the drops of a liquid are spherical because of a given volume. A sphere has minimum surface area. To increase the area of surface, some work has to be done against the inward pull. For example, consider a soap solution film contained in a rectangular wire frame ABCD in which the side CD is movable, figure 2.16. In order to extend the surface area of the film, the movable wire has to be pulled from position CD to position EF. Thus, some work has to be done against the force of surface tension. The work in ergs required to be done to increase or extend the surface area by 1 square centimeter is called surface energy. The unit of surface energy are therefore ergs per square centimeter, joules per square meter. That is joule meter minus 2 in a SI system. Surface energy is equal to work per square centimeter is equal to force into length per square centimeter. is equal to dynes into centimeter upon centimeter square is equal to dyne centimeter minus 1 or dynes per centimeter. These units are same as those of surface tension. Thus the surface energy is same thing as surface tension. Hence the definition of surface energy is sometimes taken as the definition of surface tension. So this was all about in this class, the session. In the next video, in the next session, I will take again I will take some points of this chapter and will complete this chapter for sure. Thank you for all of this.